All right, welcome. Today, we're going to pull back the curtain on machine learning. We're going to look at how these models actually go from learning something to, doing something with that knowledge. And we'll tackle a really important question. What if a model is perfectly accurate, but it's still unfair? Let's dive right in.
So it really all boils down to this one big question, right? How does a machine actually learn anything? It can feel like magic sometimes, but it's not. And to get to the bottom of it, we're going to start with an analogy. And it's probably not the one you're expecting.
Okay, so here's the game plan. First, we'll cover how machines truly learn. Then, we'll talk about training versus inference. Think of it as a model's two-stage life. We'll touch on foundation models, gauge model confidence, and get into what the right fit really means. And we'll wrap up with a tough one, when accuracy isn't fair.
All right, section 1, how machines truly learn. We're calling this one the toddler and the shark. Now, to really get how machines learn, just imagine this. You're trying to teach a toddler what a shark is, right? You're not going to bust out a biology textbook. Nope. You're probably just going to grab a picture book.
Well, in the world of machine learning, that picture book, that's what we call training data. It's this huge collection of examples. Could be images, could be text, could be numbers, and it's basically the model's textbook for learning about the world.
But, just flipping through pictures isn't enough, is it? You have to point to the picture and say, look, that's a shark. And that right there, in machine learning, that's a label. It's the correct answer that gets attached to every single piece of data, so the model knows exactly what it's supposed to be seeing.
Okay, so after you've shown the toddler, or the machine, enough pictures of sharks, something amazing starts to happen. It starts connecting the dots. It sees the fin, the pointy teeth, that classic shape. That's pattern recognition. It's that aha moment. The model isn't just memorizing photos anymore. It's actually starting to grasp the whole concept, the very essence of sharkness. So, our model has studied its picture book. It's learned what a shark is. But here's the thing. A model's life is really split into two completely different stages. You've got the learning part, and then you've got the doing part.
So let's break that down. First, you have training. The best way to think about this is studying for a test. The model is just hitting the books, learning from all that labeled data we gave it. Then you have inference. This is it. This is test day. The model gets brand new, unseen data, and it has to use what it learned to make a prediction. No more studying. It's time to perform.
Now, it's really important to know that not every AI model starts from zero, like our little toddler with the picture book. A lot of the really powerful AI tools we use every day, they're built on the shoulders of giants. And these giants are what we call foundation models.
So what's a foundation model? Okay, think of it like someone who just earned a PhD. They have this incredibly vast general knowledge about the world because they've studied an unbelievable amount of data. Now, a company can come along and hire this PhD graduate and give it some very specific training for a particular job. That process? That's called fine-tuning.
You might be wondering, well, why doesn't every company just build their own? And the answer, in one word, is money. A lot of it. We're talking over $1 million, and that's just for the computing power to train one of these things from scratch. So, yeah, it's something that only a handful of really big organizations can even attempt. So the big names you've probably heard of, things like GPT or Llama, those are a type of foundation model called a large language model, or LLM for short. They've been trained on just insane amounts of text from all over the internet. The best way to imagine their brain is like a giant control panel with billions, sometimes even trillions of tiny little dials. We call those parameters. And the entire training process is just about tweaking and adjusting all of those dials until the model gets really good at one simple thing, predicting the next word in a sentence.
Okay, so let's move on to how these models actually give you an answer. Because it's not just a simple yes or no. A model expresses its prediction with a certain level of confidence, and it really all just boils down to probability.
Basically, a model spits out a score, a number between 0 and 1. So, if we showed a picture of a great white shark, it might say 0.98. That's super close to 1, so it's basically screaming, yes, I am confident that's a shark. But if you showed a dolphin, it might give you a 0.03. That's close to 0, which means it's really confident that it's not a shark. And what about a super blurry underwater photo? You might get a 0.5, which is pretty much the model shrugging its shoulders and saying, honestly, I have no idea.
All right, this next part is absolutely crucial. It's one of the most important ideas in all of machine learning, and it's called model fit. You can think of it as the exam taker's dilemma. It's this constant challenge of learning just the right amount to actually be good at your job. Not too little, not too much.
So what does a good fit even mean? Well, a model gets a gold star if it can do two things really well. Thing one, it has to actually learn the patterns from its training data. That's the easy part. But thing two, and this is the big one, it has to be able to take that knowledge and use it to make accurate predictions on brand new data it has never seen before. That's the real test.
Now, there are two classic ways a model can totally bomb this test. First up, we have distracted Dan. This is underfitting. Dan, well, he barely glanced at the textbook. He's so unprepared that he fails the practice questions and the final exam. The model is just too simple. It didn't learn enough. On the other end of the spectrum, you have photocopy or Phil. This is overfitting. Phil didn't learn the material, he memorized it. He can ace the practice test because he just copied all the answers. But the second the real exam asks a question that's even slightly different, he's completely lost. The model learned the noise, not the signal. What we're aiming for, of course, is the balanced model. It's studied just right. It understands the core concepts, so it does well in the training data, and more importantly, it can generalize to ace the final exam too.
Okay, so we know our goal is to build that perfectly balanced model, the one with a good fit. But what happens when that model is trained on data that comes from our own imperfect, biased world? This leads us to our final and maybe most important topic. It's the problem of bias. Because even if a model is technically perfect, that doesn't automatically make it fair.
This is probably one of the most important things to understand about AI today. Accuracy does not equal fairness. Let me say that again. Accuracy does not equal fairness. You can have a model that is, by all technical measures, making the correct predictions based on the data it was given. But in the real world, those predictions can lead to outcomes that are deeply unfair and even discriminatory.
So, where does this bias actually creep in from? Well, there are a few main culprits. A big one is just biased training data. Imagine a hiring model that's trained mostly on resumes from men. It might just never learn what a qualified female candidate looks like. Then there's historical inequality. Think about it. If a model for bank loans is trained on data from a time when certain groups were unfairly denied loans, the model will just see that as a pattern and learn to replicate it. And finally, the algorithm's design itself can be a problem. For example, using something like a zip code might seem neutral, but it can often act as a stand-in, a proxy, for things like race or income, and bake bias right into the system.
And all of this leaves us with a really tough, fundamental question to chew on. If a model has a perfect good fit for a world that is itself biased, is that really a good model? This right here is the central challenge for everyone working in AI today. It's about trying to bridge that massive gap between what is technically accurate and what is ethically and humanly right.